Hello. So let's go over recursion really quickly, and let's try to understand how we can do recursion like behavior using stacks and specifically branching recursion. So I'm gonna go to my iPad. So here we have two programs and they essentially do the same thing. The one on the left, this one right here, uses recursion. No, sorry. This one right here uses recursion to print all of the binary numbers given a link that you pass in. So the output is right here. And we have another way of doing the same thing where we print all of the possible binary numbers for linked k, which is right here. But this one doesn't use recursion. It instead uses a loop using a stack. And both of these types of recursion are something called branching recursion. So what I mean by that is there's something called so if you guys remember what a tree is. So a tree is essentially we start off here and then our code can branch off and our code can branch off, branch off, branch off, and branch off. And we essentially use recursion or stacks in this manner to basically start here and do a depth first search. So we basically always search in the deepest node first, and then we loop back, and then we explore the other branches. And then we'll loop back and go here and essentially explore all of the possible nodes in something called DFS, which stands for depth first search. So that might be a bit confusing, but if I was to draw it out and trace to you how this code works, it'll become more apparent. So here we have our recursive implementation of printing all of these numbers here for given length 3. So let's trace it through, and hopefully this tree search will start to make more sense. So I'm gonna start drawing out the recursion stack as well as the tree that we are going to explore. Following along with these two concepts, I do feel like it will help you to understand how recursion actually uses stacks internally, and that's what really allows us to use that's what really allows us to do this branching. And the beautiful thing about stacks is because they also use the same internal abstraction, we essentially can replicate the same behavior. And this will become apparent as I trace. So basically, I want you to really pay attention to the stack part right here, because that's what's going to control how we're able to do something called backtracking, where we're able to go here and then go back to where we were. Okay, enough confusing theory aside, let's start tracing. So here we're going to pass in k equals 3. No, Siri, I do not want you. Okay, we're going to pass in k equals 3, and we're going to start off with a string that's empty. Okay, so first we're going to go here and we're going to do a check. Is k equal to 0? The answer is no. So basically, what we're going to do is, so actually first, once we enter this recursive function, our string is empty, right? So we're basically going to start off with a string that's empty, and it'll just be like that. And then our k is also, k is equal to 3. Cool. So then we're going to call this function right here, which is going to call the same function again. and make k equal k minus 1, and our string is going to have 0. So we're going to pop in a new stack frame. Our k is now equal to 2, and our string now has a 0. And then this is going to get evaluated, and k is still not equal to 0. So then simply this is going to get called again, and k is equal to 1. And then we're going to add another 0. And then this is going to get checked, which is false. And then this is going to get called yet again. And then here our k is equal to 0. And our string is 3 zeros. And then this will then finally be true. And our string will get printed to the console, which is right here. So let me draw out the tree we're essentially building. So each level of the tree is going to be a k. So k equal 3, k equal 2. Let me move this over here. K equal 1, k equals 0. And maybe I can color this. Probably shouldn't make it really big. Cool. Okay, so we start off, and we're going to make a new node. And then here, also, what I'm going to do is I'm actually going to include, okay, so this is 0, and I'm going to make a new node, and this will have another 0. So basically all I'm doing is I am just drawing this out in a different method. New node, so k is equal to 1, 0, 0. And then lastly, a new node. And then, yeah. So basically, what ends up happening is we start to build it up. So k is going down, and our zeros are being added. And then eventually, our base case is hit, which will print this out. So that gets printed as 0, 0, 0. Cool. So something to keep in mind here is that as we were going through this, we were always pausing right here. And you have to keep in mind that for a function to terminate, it has to reach all the way to the end. So basically, this piece of code is still yet to run within all of these stacks right here. So for all of these stacks, this piece of code is yet to run. So keep that in mind. So essentially, when you get to here, we are basically, yeah, when we get to here, our base case gets printed, and this does a return, and it essentially gets popped off. And I can remove that. Boop. And now we're back here, and remember how when k was equal to 1, it stopped right here. So now we are going to simply print out we're going to advance to the next line, and we're going to do the same thing here. And now this is going to execute. So we're going to add in one more thing to our stack. And remember here, k was equal to 1. So we're going to do -1 from k again, and now k is going to be equal to 0. But this time, rather than adding a 0, we're going to add in a 1, just like that. So essentially what's going on here is we're starting to backtrack. So because of the fact that we were able to pop this off, we had all of these functions still queued up over here. So that's how we get the history of where we've been. This is what really enables the branching part of recursion and essentially allows us to backtrack through our tree, which I'll show right here. So this gets printed off, and then we're back here, and each of these functions has two parts. One of the parts is this one, and the other part is this recursive call. So now that we know that this has executed, we're then going to execute the second part, which is going to add a 1. And that will hit the base case, and then we will print a 0, 0, 1. And that's also what is shown right here, a 0, 0, 1. And then essentially, now this k equals 1 case right here has had both of its recursive functions ran, so now it's fully done, and it will finally hit the end and then go back to when k was equal to 2. So what happens is that this gets popped off, and this also gets popped off. And then we're back here when k was equal to 2. So this is all done. And now this left-hand side is also done. And we're going to go here and we're going to branch off, because remember, when k was equal to 2, we had just stopped right here. I'm just going to erase so it's a bit easier to see. So when k was equal to 2, we had stopped right here, and now we are going to execute this. So this also has to run for this call of the recursion. So we do the same thing over here, and instead this one minus k by 1 and then adds a 1. So you do 0, 1. So a new recursive call is added, k is equal to 1, and now it becomes 0, 1. And then the same thing happens again. It goes here, it does a check, that's false, and then it goes here, and then it minuses k by 1, but it also adds a 0. And then this will get printed and then popped off. So let me add one more. And then hopefully you guys will start to see the pattern. Essentially, it just keeps on doing this again and again and again, and we end up getting all of the possible combinations. So this would be 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, and then 1, 1, 1. Which is exactly what happens here. Okay, so let's take a step back and really analyze how this really happened. How was it able to know what we've done and what we haven't? Well, the thing is, like, we have this history of all of these functions that are just waiting to complete. And then what ends up happening is that things are getting popped in and popped off and popped in and popped off. And then eventually these ones, the deeper functions will get popped off and the new ones will become popped in and those will become popped off until lastly this function right here is fully done executing and then everything is really popped off. So that's how normal recursion works, and it's able to backtrack because it has the memory of the previous states within its stack queue or the stack. So now let's try to trace over how the stack was able to do a similar thing, but without using recursion, but just still using the same underlying concept. And this is also my first time tracing through it, so bear with me here. So here we have a k, and let that k equal to 3. And we're going to make a s, and then for the s, we're going to push in an empty string. So this is a stack that takes in string data types, and we call it s. And for this s stack, we are going to push in a string that's empty. So here's our stack, and we're pushing in an empty string. So this code will then run. It says while s is not empty, so we do a check. Is our stack empty? It's not. Then we make a new string called cur, and cur is going to pop off whatever was in our stack. So basically, we have a string called cur, and it becomes whatever we pop off. So just for demonstration's sake, I'm going to put cur to the right. So it will pop this off, and our cur is now equal to that. So it's going to check, is cur the size of k? So remember our k is equal to 3. We're essentially going to check, is cur size 3? Well, the answer is no. Cur is size 0. It's empty. So what we're going to do is now we're going to push into our stack whatever cur was plus a 0, and then whatever cur was plus a 1. So we're going to make some duplicates. So cur plus a 0 and cur plus 1. And then these two things are going to get pushed in. Let me see if I can properly... Cool. So the first thing that gets pushed in is the 0, which is what's happening right here. And then cur plus 1 gets pushed in. So this is happening to our stack right now. We have a 0 and a 1. So then we go back to this loop and we check, hey, is our stack empty? And it's not, because it has 2 elements in it. So we go here and we make cur equal to whatever we pop off our stack. So let's do that again. Let's pop this boy off. And put into cur. So now it's going to do a check. Is cur size equal to 3? No, it's only equal to 1. So we're going to basically push in whatever cur is plus a 0, and whatever cur is plus a 1. So cur plus a 0, and then cur plus 1. And we're going to push those two in. Boop. And boop. Cool. And then the code loops over again, and we do a check. Hey, is it empty? It's not. And then we make cur equal to whatever the top element in our stack is. So we pop that off, and the cycle basically repeats. Oops. Cool. And we check, hey, is cur equal to size 3? No, it's not. It's only equal to size 2. So let's push in cur plus a 0. So let's do the same thing again. Zero. And then the other one is going to be a 1. So this is pushed in. Oops, I forgot this thing. And then this is also pushed in. Cool. And then the cycle repeats. Is it empty? It's not. And we make cur, and we pop off the top element and make that equal to cur. And then lastly, we do a check. Is it equal to 3? It is. So all we're going to do is we're going to print out cur, which is what happens right here. The 1, 1 gets printed. And then this is now ignored. And we basically make cur equal to whatever we pop off. So this gets printed, it gets deleted, and then we pop off this one. And then we do a check. Is cur equal to 3? Oh wow, look, it is. It's 1, 1, 0. So then this gets printed, and this gets ignored, and then we pop off cur again. Whoop. So the main point here is that these two elements, once they're made, they are staying in memory. And this is the big point here to understand between recursion and a stack. A stack contains memory. A stack contains all previous iterations that you were building up to before you hit the base case. So as your function starts, it starts to build up towards the base case, and then once it hits, it will return to the function that calls it. And this function still has its memory. And then the function will execute, and it'll hit the second line, and then print this, and then it will go back here. And when this is done, it will go back here, which is also stored in its memory. So see how this is stored in its memory still? So we'll go here, execute, execute, and then everything will stay in the memory for as long as the function isn't fully executed. So this is what gives recursion its memory. And this is what allows us to do branching and back tracing to us. That allows us to remember where we were. So this is the beauty of the stack data type, is that it really contains memory of where you've been. And this is essentially what we're taking advantage of. So stacks do it a bit differently. Rather than having the function keeping on calling itself, we basically keep on pushing in and popping off in the stack until we've hit the base case. So the base case here would be right here. This is our base case. And then we keep on pushing in stuff until our base case is hit, and then we always pop off. So the concepts are pretty similar. They both contain memory. It's just that this one does it just by calling functions of itself, and this one just does it using a while loop, and it will keep on running until every single possibility has been exhausted. So let's keep on tracing this, and hopefully you'll see how the other possibilities are being exhausted. And how we know that all the possibilities will be exhausted is that the thing is, like, these two functions, they do add in extra paths to explore. So this push function adds in a new stack frame, and then our stack remembers what we've pushed in. And then this one also adds in another stack frame, but with a 1, and it also remembers what we pushed in. So this naturally explores all possible combinations, and it always goes to the deepest node first, which is the base case, which is 1, 1, 1, and then it goes back, and then it does all of the others until the program is completely satisfied. So it starts with 1, 1, 1, 1, 1, 0, and so forth. And then it finally stops once the 0 is fully exhausted. Like once the 0 is fully satisfied, and the 0 will be fully satisfied when we print 0, 0, 0. Okay, so let's keep on continue tracing. But yeah, try to remember that it has its own memory because we're adding into the stack. That's the big concept to understand here. And also, I recommend just practicing, and you'll start to build an intuition, which is what I'm kind of doing right now. Okay, so where were we? Where were we? We printed off a 1, 1, 0. Cool. So now we're here, and we check, is it equal to? Nope. So we essentially, I think we popped this off. I might be wrong here. We pop this off, and then we pop in, push in 2 more elements, and we do current plus 0, current plus 1. So we push in. So let me duplicate this. Actually, I'll just erase, so it's a bit easier. So we're gonna make a new one. So we popped this off. And I'm going to make 2 duplicates of it. And one of them is going to get a 0 added. And then one of them is going to get a 1 added. And the 0 gets pushed in. The 0, 1 gets pushed in first. And then this one gets pushed in. And then we read it. So this is equal to 3, this is equal to 3. These two get printed, and they get popped. And then when these two get popped, we are back at our base. We have now fully satisfied the we have fully explored all of the nodes that were tied to this branch over here that was 1 and 0. So let me just build up the node tree so it's understandable as well. Can I copy this? So here, instead, we're looking for string length. Actually, that was kind of a waste of time. I'll just fully erase it. Start over. Cool. So here, what we're doing is we're looking to make sure that k equals to 3. So our base case or our like print case is when k is equal to 3. So we start off, when our size is equal to 3. Cool. So we're going to start off with size 0, size 1, size 2, and size 3, and I'm going to color code them. Cool. So what ends up happening is that we start off with our string, which is empty. And then what we do is we start to add in a 0, and we also start to add in a 1. So the way that this tree is built is kind of different. So here, what happens is then you go here and we add in a 0, 1. Sorry. Actually, no, it'll be flipped. So we add in a 1 and we add in a 0. And then here, what happens is that we push in these two. So here, we'll add in a 1 and a 0. And here, we'll add in a 1 and a 1. Cool. And then we haven't hit the base case, so we keep on adding in 0s and 1s. So here, add in a 1, 1, 0. And here we'll add in a 1, 1, 1. And then these two get fired off. So this gets printed, and then this one is fully satisfied, and this gets popped off. And then we go back here. So it gets printed, once that gets printed, and then this one also gets printed, and then we go here, and then this is built up again. So we do 1, 1, 1, 0, 1, and 1, 0, 0, and that's printed and then popped off. And then we go here, and like the same cycle essentially repeats. I'll probably just draw it fully out. So the way that the graph is, I feel like the way that the graph is built is actually pretty similar, but between these two, like recursion just goes straight here first, and then it goes there, and then it goes there, and then it goes there. Whereas I feel like with stacks, what's really happening is that we start off here, we build them both up. So we're essentially like, rather than going like straight for the deepest node, we're essentially we're doing like um we're building up the tree with breadth instead of depth. So DFS versus BFS. At least that's what I think is going on. So we're kind of building up the tree like this. And then yeah. So we're building it up at one node well, actually no, it is still depth first search, yeah. But it's just slightly different. Like it's still we're still gonna build up the deepest node first. But with recursion with stacks, these guys are built up and are conveniently fired off right after. Interesting. Cool. And I also think that we so we're doing more work, but we fire and burst. But we hit base case and burst. Whereas here we are really just doing one recursive call and trying to hit the base case each time. Yeah, that's actually pretty cool. It's pretty interesting. I think that what we have to do is we all have to do a push and a pop. Always a push and a pop. But in what order? Yeah, I'm actually kind of curious. I'm actually gonna Google that up. Like, is it that we need to? Yeah, so this is how it really works. Well, the stack is not empty. Mark it as visited. Push it, it's unvisited. Yeah, it is a bit more complicated for sure. Yeah, so depth first search using recursion is simpler, more concise. DFS using a stack is harder. Yeah, but I guess we just need practice. Not impossible. Homework questions. Cool. Yeah, I hope that kind of helps. I personally need to practice a lot. That's why my explanations weren't so great. But yeah, this is also like a revision for me. Anyways, yeah, take care.